Welcome back. So here is a test basically on the introduction to functions. So it's kind of directed towards grade 11 students, as I always do with these tests at the end of the chapter for all the videos. I'll put this test up so you can download it for yourself in the show notes. All right, so if you're having trouble with the link, just leave a comment. I'll follow up. And try to download it, solve the test, and then come back and then watch the solutions, which is what I'm going to do right now. Okay, so let's get started. So question number 1, I kind of copied it down right here for myself, and it has numerous kind of sub questions within here. So the first one is, how do you know a relation is a function? One of the most common things that students kind of remember about this is because they test functions by a vertical test. Right, so whenever you have a relation, you can always graph it, and you can graph it. So here is, let's say, your dependent, and then here is your independent variable. Now we typically say x and y. And what students will do is, so they will simply say, okay, so I can do a vertical test. So, I can create this vertical line, and then what I'm going to do with this line is I'm going to move it around to make sure that whatever ordered pair that I have on this graph does not have multiple outputs for the same input. So for example, you will not have something like this happening. And that is fine, and that's a very visual test. We do use the vertical test, especially when we have graphing. But what does that actually simply mean? It just simply means that for a given input that you have, or for a given independent variable that we're going to be working with, we only have one output. For a given input, we only have one output. And if you're going to use this as an ordered pair, so let's say we have x1 and then the representing relation, so this is a relationship between x1 and y1, that you only have one of them. So what cannot happen is, you cannot have another x1, which is exactly the same thing, and then you have a different result right here. Because what that would mean is, so for example, if this was x1, this was your y1 value, and then this was your y2 value. And then you have a problem because it's not unique. So how do you know, in your relation between one and the other, which one should you use? Now, they do happen. We certainly have those kinds of relationships, but if it happens in this way, then it's no longer a function. So to answer this question, how do you know a relation is a function? I typically like to say that for any given input or for any given independent variable that you have, for its value, you only have one value for its output, which is going to be the dependent variable that you carry. All right, so that's kind of how you can think about these particular functions. Let's take a look at number 2, or B, right here. Are all relations also functions? Well, no, right? Because you can have relations that are not necessarily functions, why or why not. Now, the reason for this is, a relation between x and y. So for instance, I can do a relationship, and we have seen these relationships, which can be, for example, mapped with a nice, simple relationship like this, which is a circle. And this circle, if I were to draw it, so it has a radius of 1. And in this case, notice that this particular circle is not going to actually pass a vertical test, right? So no matter what I do, if I would take this line and I would shift that line over, so let's say right here, I run into a problem that, hey, wait a minute, I have 2 values for only one single value of x. And therefore, this is a relationship. It's very legitimate, but it is not a function. All right? So here, to answer this, are all relations also functions? The answer is no. And why not? Because you can have relationships, that do have multiple outputs for a given input. And an example here, it says, well, I guess a circle is an example of that. Or you can make a relationship very simple, much simpler even than this. You can do a table of values for your x and your y. And then you can say, for this one, I have an output of 2, and then I have another one, and I have an output of 3. This is the simplest relationship that you might have, and you will have multiple outputs. So it's just going to be 2 points if you would plot them up, but it's not going to be a function. But it certainly is a relation between x and y. Now, I made it up, but that's an example. Let's take a look at part C. So in part C, it says here, so create a restriction on the range of the circle. Now, this circle is a relation, so x squared plus y squared equals to 4, such that it becomes a function. Well, what relation, or maybe, what it says here, I guess it doesn't really say, so create a restriction. So it doesn't really force you into any particular restriction. So you can do whatever restriction you like. But to make it a function, so this has, so if I'm going to plot this up, let's say like this, and I'm going to do the circle. So the circle basically has a radius, I guess, of 2. Okay, so it crosses here at 2, and 2 is going to be -2, -2. Now, what can I do to make this, I guess, a function? Now, because it doesn't really restrict it, I'll try to find the biggest restrictions. Okay, so within here, we can certainly make this. So for instance, if I would only take this half circle right here, and I don't take the upper bound, so I'll only take this one from here to here. And so for that, I can create a restriction. Now, I would have to create a restriction on the y. So for example, here, I could create a restriction such that my y is going to be, say, between -2 and 0. And 0, of course, is my line, or sorry, my point for the y. Okay, so 0 would be right there. And what I would have is this restriction that I would carry. It would only be, okay, between 0 and -2. And this indeed would be a function. So it wouldn't take the upper, okay, part of this circle. Now, you can also create other restrictions, of course. I mean, you could take the upper circle and you can say, well, what about this one? Does this restriction work? And the answer is yes, this does work. It would take the upper circle, okay? Now, you can create other restrictions. You can take a quarter of a circle or a piece of a circle or something like that if you wanted to, but you have to be careful. Now, the restrictions are going to have to be on y, because if you start taking restrictions on your x in here, then unfortunately it will take the top and bottom and it will still not be a function. All right, so those are 2 examples. Now, you can choose other ones if you want. All right. Okay, so that's the restriction there. Now for part D, so for the relation, so now here we have a square root. Find the allowable domain and state if under that domain the relation is a function. So y is equal to, so let's take a look at that. So y is equal to, so this is the square root of x minus 4. Now, for this, so allowable, so that means within here, well, we have a square root. So we know that x minus 4 has to be greater or equal to 0 because we can't have negative values under the square root. And so for that, okay, that's what we have. Now, in this particular way, so the way that this works, so you may recall, so this is kind of the parent, right? So this is the square root function in general. So how does this look like? So this kind of looks like this, right? So it looks like kind of like that and keeps going. Now, for this, okay, so for this right here, if we're going to graph and we only take the positive values, and do not take the negative values, right? Because I guess, the square root, we could also take these. If we take both the positive and the negative, then it's not a function. If we only take the positive, that's typically what we do in math. Whenever we see a square root, we just take the positive just to make it really a function. So for this, under this particular restriction, if we only take the positives, then it is a function. It will easily pass the vertical line test because there's going to be only 1 point for every single input x. And so what does this mean? Now, of course, we don't have this. We have this shifted over. So this is -4. All right. So what does that mean? So from here, so this just simply means x has to be greater than, and in this case, it's going to be greater than 4. All right. So how does this look like? So this just gets shifted over, and it's going to start at 4, and it's going to go in this direction. All right. So it's going to look like that. So it's basically just a shift over. And notice for the values of, for example, 3, if you substituted 3 in here, then you'd get 3 minus 4, which is -1, and we can't take the square root. So our kind of domain for this, under the restriction, it's going to be all the values which are equal to 4 or bigger. All right, so that's what we have there. Now let's take a look. So the next one, what does this represent? So this is a composition of functions. I like this. How can you represent it in an equivalent way? Okay, well, the symbol itself, so if you're going to do this, so f and then g of x, okay, so the exactly equivalent symbol for this, sometimes we write it with this little f of g, kind of like that. All right, so you can kind of write it like this. It's a composition of functions. Now, what does this mean for us? Okay, so what it means is you have an input x. So here's an input x. It is applied to some g of x. Okay, so then you have an output, which is y. And that output, okay, goes into your f and whatever, if it's a function or a relation or something like that. Okay, and then it spits out your overall answer, and then your overall answer is just simply f at g of x. All right, so that's what we have there. So don't forget. So basically, there's two things happening in here. You're applying g, and then you're applying f. All right, and if you like, you can remove the y and then put the y over here because that's your final output that you have. All right. Now, next, what is an asymptote? Okay, well, what is an asymptote? Okay, so for that, if you had to write it in, I guess I'm not going to kind of write it. I'll just speak about it. So an asymptote is basically a line, right, on a plot, okay, that you have. So let's say on an x and y plot. And it can be any line. It can be a horizontal line. It can be a vertical line. It can be a line with a slope. And your function is approaching that line. So it's approaching that asymptote, but never touches it. So an asymptote is a line for which a function approaches, but never touches. So that's what an asymptote is. Okay? And too bad it didn't say any examples. Okay, but we have seen many examples of this. One of the nice examples that we have is, if we have, let's say this, okay, which is the reciprocal, and we know that we have two asymptotes in here. So this kind of looks like this, and it looks like that, but it has an asymptote at x is equal to 0, and it also has an asymptote at y is equal to 0. So our actual function approaches those two lines, but they never touch it. Okay, so those are kind of examples. All right, so what else is here? So that was a lengthy question 1. Question 2, let's copy this one. So from the given table, so we have kind of small little table in here, so this hopefully won't be too difficult for us. So let's see, so it's not in kind of graphical form or anything, but okay, so here's your x, here's your y. So here's all the relationships between them. Determine if the relation is a function. Okay, well, we just said that for a function, so we have to make sure that for every input, you know, we have a unique output. And here, so what do we have? We have 3, so 3 is 0, 0, 4, negative 2, 1, 1, 3, yes. Okay, so it is a function. So it is a function, and why it's a function? Because for every single, so for part A, okay, so for every single ordered pair that we have, notice, so if we're going to take all of these, then we have 0 and 4, okay, and so on. So for every input that we have, we only have one single output. So that's why. All right, so this is great to be able to see. Now, construct a table of values for the inverse. Well, the inverse is simple. So remember, for the inverse, what we do is we just swap the x and the y. So in that case, what we would do is, so I basically have to swap them. So x, y, so that's going to be that, but I have to swap it. So I'm going to take 0 as my x, this is my y, so that's 3. 4, this is going to be 0, 1 is negative 2, 3 is 1, and 0 is negative 1, and that's a problem right there. Notice 0, 3, 0, 1. So you have, for the same input, so what you have for the 0 and the 0, you have 2 outputs. So that can't be a function. Is it a function? No. And the reason is that because for the same input 0, you have 2 outputs, negative 1 and 3. So that would have been for part B. All right, so that one was much simpler. So that's what we have there. Now for question number 4, so let's take a look here, or sorry, question 3. State the domain, range, asymptote, and inverse if it exists for each. Ooh, okay. Well, let's take the first 2 right there. I'm going to take these, copy them. Actually, I can do them right here. So the first one, so notice y is equal to 3x minus 2. Well, that's a line. So right away, we know that lines will have inverses. There's only one line that doesn't have an inverse, and actually that's going to be part B. So this one, as long as you have a slope and the slope is not 0, okay, so for that one will be fine. But we do have a restriction, so let's take a look because it's asking us for domains and ranges. Okay, so in order to find the domain, okay, because this restricts our range here between 0 and 3. So since it gives us that, so the range, okay, would be, so y is a real number such that, okay, but it is being restricted. Okay, so it's only allowed to be that. So that's the range. Remember, the range has to be a set. The domain x, okay, is also going to be restricted. And now let's see. So for the value of 0, so if I plug in 0, what does that give me for my x? So let's shift this over. So 2 divided by 3. So x is going to be, okay, so let's see. That's the first one. And then on the 3, so if I substitute that, so I'm going to get 3x minus 2. So that's going to get shifted over. So 3 plus 2, so that's 5 divided by 3. That's x. Okay, so x is going to be between these two bounds. So 2 over 3 and 5 over 3. Well, 2 over 3 is the smaller one, so 2 over 3, and x is going to be 5 over 3. Just make sure that your inequalities, so because it's, so here, it's not equal to the bounds All right, so just keep them like that. So that's the range and then the domain. Now, if you want to find the inverse for this, so we're going to have to solve for x, right? And then just swap the x and the y because it's just a line. So that's not very hard to do for us, I hope by now. So y plus the 2 is equal to, so I'm just solving for x. And then I'm going to divide by 3 on both sides. So I'm going to get x, y over 3, and plus 2 over 3. Okay, now I'm going to swap. So the x and the y will swap. So my inverse right here, y is equal to, actually let's write it like this. That's an inverse. So the inverse is going to be this line. All right, so that's what we have there. Now, does that inverse actually have a domain? Yes, it will, and it will have a range because of the fact that I had a restriction here, right? So the inverse can't exist for everything. Now, because we're swapping the x and the y for lines, you just swap also the ranges and then the domains. Okay, so that's what you're going to have. And I do encourage you to also try to graph it and then see that it is a reflection in the y is equal to x, okay, for the inverse. So that would have been the first example. Now, in my second example, so this one is interesting, the y is equal to -2. So just for that one, if I'm going to try to do that, so y is equal to -2. So this one's going to be interesting. So the domain in here, so because there's no restriction, so the domain, I'll just write d, will be basically anything. So any real number. So that's what we have. The range, well, the range is actually going to be only y is equal to -2. Because that's what this relation is. It just maps everything to -2. So it's just a flat line at -2. Now, the inverse, okay, so if this is a flat line, right, at -2, this is your x and your y. Yeah, sorry, so this is, let me remove this. There's your x above, because this is at -2. So what does that mean? That my inverse, because we're swapping x and y's, so my inverse is going to be just a straight line up at x is equal to -2. Okay, so my inverse would have been this line. It's just a vertical line. But a vertical line, we know, does not pass our line, kind of vertical line test, so this is not a function. All right? Okay, so we can't say that this particular inverse is a function. Now, it asks us about asymptotes. Now, these ones don't really have any asymptotes because they're not approaching anything, they're just lines. So they're already a line and they're not approaching a different line. So that's part A and part B. Now, part C and D looks a little bit uglier. Let's copy this. Let's see what happens here. And I'll paste it in here. All right, so for part C, the domain, so we have basically a denominator. So we know that when we're dealing with denominators and we're trying to find domains and ranges, well, for the domain, we cannot have the denominator equal to 0 because in this case, we would get 1 divided by 0 and that would blow up. Now, this one is actually not bad because notice x squared minus 1. So that's just difference of squares. So this is x minus 1, x plus 1. So that's what we have there. So we know that x cannot be equal to 1. And we know that x cannot be equal to -1. Because if it will be, then we're going to get 1 over 0. And that's undefined. So our domain in here, so that's any value that we have. However, x cannot be equal to -1 and it cannot be equal to 1. So that's the set. Now, what does that mean for the range? Because the range is much harder sometimes to find with these. So we do have a quadratic in here, right, in the denominator. So what will happen? Now, the problem will be what's happening near these guys. Okay, so first of all, in order to find this, now, of course, you can graph it, kind of cheat a little bit for yourself and be able to see what's happening. I'm going to try to intuitively think through this. Let's say if you weren't allowed to graph on a test, and you were sitting in a classroom, so what would we do? Or at least how could we approach this? So the idea is, okay, so here is this is your g of x, and then this is your input x. All right. Now, what happens on the far ends? We know that at 1 and at -1, so these are going to be some asymptotes. So something is going to be happening within here because we cannot come close to it. So, all right, let's imagine, so first of all, if we are trying to work with x kind of in this domain, so in this right here, and then we're going to see what happens if we're working in here, and then we're going to try to figure out, play around with the one between -1 and 1. So clearly we do not have x is equal to 1. So just, as x approaches to 1, okay, from the right side, what is going to happen there, right? Now, it's bigger than 1 just by ever slightly. So what is going to happen is you're working here with this. If this value is, so if let's say if it's 1.001, and you're getting closer and closer to 1, okay, coming in this direction, then if you're substituting it into here, so that's going to be, and you square it, it's going to be a little bit bigger than 1. So you're going to have a little bit bigger than 1, -1, which is going to give you a very small number, right? Because it's going to be 1.00, whatever it might be, -1, which is going to give you just a tiny number. 1 divided by a tiny number, okay, becomes a huge number. So this means that this is going to be exploding in this direction like this. Now, what happens to it was you get x gets bigger and bigger and bigger, right? Well, again, so what's going to happen, this -1 right here is, this -1 is going to be irrelevant if x is very big. And as it gets bigger and bigger and bigger, then what you're going to have is you're going to have a huge number at the denominator and 1 on top. So that means that this is going to be going basically to 0. But it's never going to approach 0. So you're going to have an asymptote at y is equal to 0 right here. So you're going to have some asymptote right there. So let me draw it in here. So there's going to be some asymptote because that will never reach that. So that's on this range. Now, we can do exactly the same thing right here. When we are approaching -1, and as we're approaching -1, okay, so here, now what we're doing is, okay, so these are negative, right? So they're just trying to get to -1, okay, getting closer and closer and closer. And now what you're going to have is you're going to be squaring that. If you square it, the negative will be gone. So again, it's going to be something a little bit bigger than 1, -1 in the denominator, which is going to give you overall 1 on top and a very small positive number at the bottom. So it looks like this is going to blow up in this direction as well. Okay, so it's going to blow up in that direction. It's going to be positive in that. Now, as you get further and further out, so you make x very big negative, again, you're going to run into that this minus 1 is not going to do anything, and it's going to be dominated by this x squared. So a very big number, negative squared, is going to turn to be a positive number. And that's going to give you that this is going to be approaching 0 from this direction. So far what we have is that our range is basically anything above 0 in those two. Now what happens in between here? So what happens in here, right? That's what we want to know. All right, well, this one will be a little bit harder to be able to see. And in order to do that, we're going to try to approach, so we're going to go in this direction. So we're going to get closer to this negative 1. All right, so we're going to get closer and closer to negative 1, but it's going to be slightly kind of bigger than negative 1. So we're going in this direction. So instead of doing this right here, what we're doing is we're getting closer and closer. So it's almost like 0.99, 0.999. Okay, 9999. So we're getting closer and closer to 1. But notice that these numbers, okay, the absolute value of them is still less than 1, the absolute value. If you're thinking negative, then it's bigger than negative 1. Which means that if I square this, it's going to be less than 1. But it's positive. So this is that. Minus 1, it's going to give me a very small negative number. All right? So take a look at that. So I'm going to take, okay, negative 0.9999, whatever, how many nines you like. I'm squaring it. And then I'm subtracting the 1. This is the denominator. And look what it gives me. It gives me a very small negative number. Now, if I take 1, which is in the numerator, divided by a very small number, it starts to blow up. But it's now blowing up in the negative direction. So it looks like this kind of is going in this direction. Now, if you're going to be approaching your x in the positive, okay, in here, you're going to run into exactly the same thing. You can test this out. So this is going to go in this direction. So it looks like my range is basically going, okay, so straight down. So now, because there's symmetry here, all right, so it's between negative 1 and 1, okay, what happens there as you get closer to x is equal to 0? As x is equal to 0, what you are approaching, okay, within here, on top you have 1, and then at the bottom, if x is approaching 0, then what you're going to have negative 1. 1 divided by negative 1 is just negative 1. So it looks like this thing is going to stop there, and it has a maximum at negative 1. Now, if you could understand this without graphing, amazing. Now, this is a challenging question for you to be able to see. So my range, okay, looks like y is going to be, okay, y is greater than 0. It never touches 0, so that's that. And I also have another restriction. My other restriction is that y is going to be less than, okay, negative 1, all right, and equal to, because that happens at x is equal to 0. All right, so let's take a look if we were correct. So now we're going to try to graph it. And now the asymptotes you see, we saw an asymptote at y is equal to 0, and now we have two asymptotes, one at negative 1 and one at 1. Okay, so let me graph this for you quick. There you have it. So it's basically kind of like we drew it out, kind of the thought process behind it. Obviously, this is much nicer than the way that I did it, but this is what you have. And you have your negative 1 and 1, and it's approaching that. That was an amazing exercise if you were able to do that, because it really forces you to understand these domains and ranges. All right. Now, for an inverse, so that, I mean, I guess this one won't be as bad. Okay, so for an inverse, what we have, let me just add a page in here. So here is our starting point. Now, for an inverse, we have to solve for x. So I'm going to, instead of g of x, I'm just going to write y, just so that it's easier for me to isolate. All right, so let me, first, I'm going to multiply both sides by x squared minus 1. So x squared minus 1. I'm going to bring the y over, okay, so divide that. So that's just going to swap. That's what's going to happen there. I'm going to bring the negative 1. So that's going to be plus 1. And now take the square root. Now the answers are going to be both positive and negative. And we know that square roots, if you take both positive and negative, it won't be actually a function for square roots. Let me plot it for you. So here the x and the y's swap. Okay, for the inverse. So maybe what I'll do is do that. So that's the inverse. But it's not going to be a function. All right, so if I would plot this, and this was square root of 1 over x plus 1, was it? I think that's what it was. And now if I want to take, again, if you wanted to see both positive and negative answers, then you have to do this. Because the plotting tools always give us. All right, so there you have it. And clearly not a function if you do it in this way. If you only take the positives, then I guess it is a function, but then it's not an actual full-out inverse. Okay. Now the original 1 over x squared minus 1, was that a function? You know, so if I hide these away, and the answer is yes, this was a function. Passes the vertical test, no problem. It was an asymptote, right? The domain doesn't exist in 2 points, but it is a function. So that's a great example for this particular test. Okay, so here's another one for you. So that's this one right here. Let me copy this and paste it in here. So that's the last one there. So finding the domain, ranges, inverse, whatever, asymptotes if necessary. So let's take a look in here and see what happens. All right, well, for domain, we always have to worry in here. Okay, for this, we don't want this be equal to 0. So if I say 4x plus 3 cannot equal to 0, this one's not very difficult to work out. This is going to be 4x cannot equal to, so, and then divide by 4 on both sides. So it cannot be equal to negative 3 over 4. So my domain for that, so x, and this is it. So that's my domain. So it just has a restriction there, so I don't know what's going to happen there for that. And now my range, just like before, it's going to be hard, right? Because we would have to kind of walk through and see what happens. Okay, so let's take a look here. What is going to be happening overall? And so if I graph this, say this is my x. All right, so we have a problem at negative 3 over 4. So something bad is happening there. Now we don't have as many sections as in the previous one. Okay, so yes, it's annoying if you want to find the actual range. Okay, but let's see if we can maybe figure it out. All right, so first of all, what happens to the left? So in this region, for this particular item. Okay, so when it's very negative, so as it's approaching negative infinity, okay, so it's becoming bigger and bigger and bigger negative. So what do we have? We have 1, so 1 minus x, and then 4x plus 3. So if x is very big, then this 1 and then this 3 won't really make that big of a difference. And what you're going to have right there, and this is very big, and then this is very big. So notice what you're going to see is you're going to have, so it's negative. Let me maybe write it like this just so that you can see the whole thing. So 1 minus, okay, let's say a very big negative number. Say, let's keep this at 1,000 for instance. So what's going to happen? So it's going to be 1. Now the negative and negative is a plus. So you're going to have, let's do that. It's going to be negative. It's going to turn into positive. Sorry. And that's going to be in the numerator, right? Now in the denominator, so we're going to have, so 4 times negative that plus 3. So 4 times that, so it's going to be 4,000. So it's negative 4,000 plus 3. Okay, so it's going to be negative 3,997. All right, so you have basically a 1,000 positive and then almost a negative 4,000 at the bottom. And if you make the number bigger and bigger, it looks like it's going to be approaching negative 1 over 4. So negative 1 over 4. So negative 1 over 4. Now, it's going to be approaching it from the top or from the bottom. And it's always going to be, because you have this plus, so it's going to be just slightly, it's going to be approaching it, so negative 1 over 4. Okay, so you're going to have, so this is a good exercise actually for us. Just thinking, okay, so it's going to be negative and it's going to be 1 and just, so let's see. So my question here is, this is negative 4. Is it approaching it like this or is it approaching it like that? Right? So from the top or from the bottom? Well, let's give it a go here. My mind is going blank, so I'm going to just put the numbers in. Divided by, that's 3,997. So it looks like it is approaching it. So notice because of that. So 1 over 4 is 0.25. Now it's negative. Now notice you have 0.4. So it's always going to be a little bit, absolute value is going to be bigger. All right. So it's going to be approaching it, okay, from the bottom. All right. Now, what happens when you have this x is approaching negative 3? So as we get closer and closer to negative 3 over 4. So what is going to happen there? Well, okay, so in that particular case, okay, so what is our denominator going to be? Now you can start substituting it back in. So we're basically, as we're substituting this in, we're going to get closer to this, like that. So we're going to get closer and closer, and now it's going to become negative, okay? Now, why is it going to be negative? Because you're approaching it from the left-hand side going to the right. So you're always going to be just a little bit less than negative 3 over 4, meaning the absolute value is going to be a little bit bigger than 3 over 4. So it's going to be going in this direction, and then therefore it's going to make the denominator, okay, so that you have there, that denominator is going to become negative. Okay, so it's going to be very, very large negative. And now on the other side, okay, so as we're going through, so as we're approaching, okay, from the opposite side, and in that case, it's going to be, so it's going to be the opposite, so it's going to be blowing up in this direction. And then, okay, as you make it very large, it's going to be going in this direction. Okay, so that's how it will look like. So it looks like the range, it has an asymptote at negative 1 over 4. Okay, so the range in here, so this is another tough one. So the range, so here's my domain. My range is going to be everything except, and y cannot be equal to negative 1 over 4, but it's everything else is allowed. All right, let's graph it, okay, to see if I was right. All right, so let's close these ones up. So we had y is equal to, and 4x plus 3. There we have it. So we were right. And notice it's approaching. Okay, so as you keep going in here, notice this value. All right, so it just keeps going and going. That's what it's going to be. And notice that here, so negative 0.247, you know, as you keep going and going, so it gets closer and closer to negative 0.25. Okay, and now in this case, so that's what we have. Perfect. So we were able to kind of estimate it more or less, kind of looked like that. And then we do have an asymptote there. I know that you hated this question, but it really forces you to try to understand these domains and ranges. So that's what we have. Now for the inverse, does an inverse exist? So if I do that, let's add a page for this one. So how would I do that? So this is 1 minus x, 4x plus 3. Okay, I'm going to call this y. And now I'm going to isolate and try to find x. So multiply both sides by the denominator. So I'm going to get this. If I do that. Now next, all right, so let me bring this inside the brackets. So I'm going to get 4xy plus 3y equals to 1 minus x. Now we're isolating for x, so we want to bring the x's over together. So this and this term together, and then the other terms on the opposite side. So 4xy plus x equals 1 minus 3y. All right, so far so good. Let's factor out the x. So 4y plus 1x equals 1 minus 3y. And now finally divide both sides by 4y plus 1. That's going to give us that, and that's our inverse. Now we swap. So our inverse, actually this was g, I think, or v or something. V, oh, this was vt. Okay, this is an error. This should be vx. Okay, so I'll keep it that, or we can write, so v inverse and 1 minus 3x all over. 4 x plus 1. All right, so that would have been our inverse. Now, an inverse is, again, it's going to, you know, for your domain and range, you can try to do, okay, the same thing. Okay, so just to kind of leave you and not torture you with that same process, but they should be swapping, okay, within there. So let's take a look and try to graph this. So I'm going to graph it up. I'll put it in here so that we can see it. So y is equal to 1 minus 3x all over 4x plus 1. All right, so this is how that looks like. Okay, so this is what we have there. So not the prettiest, okay, but that's what it would be. Okay, so if I blow this up, this is what you would have. And then, so your y is equal to x. Okay, so this is, let's see, let's do that. So you can just kind of see the symmetry there much nicer, okay? So there we have it. Okay, so now you can see the symmetry between them. Okay, so the purple one and then the black one. So there it is. That's the inverse. Now, the inverse also has some asymptotes, but they didn't ask us about that in the question. All right. So finally, so this brings us, I guess, towards the end, okay, to questions 4 and 5. And hopefully these ones won't be as crazy for us. So this looks like it's transformations. Now, with regards to transformations, let's go in here, paste it. So question number 4, given the parent function, so 1 over x, okay, so we know that. Explain what transformations the following would cause. Estimate a graph by hand and then graph using your favorite graphing tool. So of course, you know, we can use decimal. So here's our parent, and let's highlight this a little bit bigger. That's our parent, and then here's the transformation. So let's write that for number 4. So negative 2f, and it says 3x minus 9. So I'm going to, so let's factor out the 3. So we put it in our form. All right. Okay, so this is what we have. And now 1 over x, so if I try to graph this, actually, okay, let's try to graph it here. It says to approximate it. We'll try to approximate it more or less. Okay, so my 1 over x we know looks like this. So it kind of looks like that. I know it's not going to be perfect, but all right. And then it looks like this. Okay, this worked out pretty nice. Okay, so this looks kind of like that. Something of that. It doesn't curve that way. It goes, you know, closer to 0. So that's our parent. And now, okay, so what would this mean? So first of all, if you did this, well, the negative means there's going to be a reflection. Now, if it's going to reflect, and then the 2 means that we're going to have a stretch, right? So it's going to have a stretched out. So this one, okay, so this is going to get reflected down. So it's going to look and stretched kind of by 2. Okay, so this is going to kind of look like that. I don't know if it's, okay, but it's going to look like that. And then stretch. And this one's going to get reflected, okay, in the opposite. Okay, so that's the first part. So this works on the y. This 3, okay, it's going to, so that particular 3, what is it going to do? That works within your x, okay? So it's going to kind of take these out and then compress them back in, okay? So both of these are going to get now kind of compressed back in, okay, by this factor of 3. I'm not going to redraw it again, I guess. Okay, but that's what's going to happen there. And now this is the easiest part because this just simply shifts. Okay, so it will shift this by 3. Okay, so it's going to shift it by 3. So this is the center. So it's going to shift this, 1, 2, and 3, and then move it up by 2, 1 and 2. And so that's going to be the central point. So now how do I do that? Let's say, so that means this will kind of look like this. All right, that's going to be that. And then this one's going to get shifted up like that. Okay, so that's how it will look like more or less. All right, let me graph it for you and then I'll come back so that you can see this thing in action. Okay, so there you have it. So I set the -2, the 3, the h is 3, k is 2. So notice it gets shifted just as we had. And then you have your reflection back out. Okay, so it looks, mine isn't as good, I guess, but you can see that it got shifted. I guess I didn't compress it, as I said, by that 3. But if you were sketching it, that would have been a pretty decent job, okay, that you would have had. So that's question number 4. You can try to see if you understand those transformation. And then your last one, question 5. Ooh, this is an interesting one. It's x cubed. We've done x squared, okay? What about x cubed? So this is going to be a little bit of a challenge. Now, whenever you're dealing and you have a parent which maybe you haven't seen before, a function you haven't seen before, you kind of should give it a try. Create a table of values for yourself, and then spend, let's say, between -5 and then 5, and then see what happens. Now, notice x cubed is just a polynomial. So the domain is everything. Right? We know that it's going to be blowing up because it's cubed, anything positive. But notice that unlike a quadratic, which was a parabola, it's not going to be that symmetrical, okay, around that y, because when you cube it and the numbers get bigger and bigger negative, and you cube a negative number, it still stays a negative number. So this is pretty neat. So I'm going to, let me copy this just so that I have it. I'll place it here. And if I want to sketch this, so here is my x and y. So this right here, at 0, it's 0, right? And now what's going to happen is, so if you sketch it, it's going to look kind of like this. Okay, it's going to start blowing up very fast because it's cubed, but then it's going to also blow up in this direction. This isn't the greatest line here, but it kind of starts going like that. So because it's cubed. So this is pretty neat. Now with this, okay, so notice that the negative just means that there is a reflection along the y. So how is this going to look like? Then that means if there's a reflection, then this is going to look like that. Okay? Where this gets reflected over there and this gets reflected over there. Right? Because it's the reflection in the y. Now, the rest, okay, so what else do we have? What's going to happen? We have, so within here, so that it's going to be -f minus, let me take this out. It's going to become positive, and then 0.2, what is that, 6? So that's going to be 6 plus the 1. All right. So now this means there is a reflection in the x. So it's going to get reflected now again. So this is going to be neat, and it's going to bring it back to the same thing, because if it gets reflected in the x, this is going to go over here, and this is going to go over here. However, that reflection, now notice it's 0.2. So 0.2 is going to kind of not compress this more in. It's going to stretch this out a little bit further. All right, so what we're going to have is it's going to start stretching it out. Oh boy. Okay, so reflection. So it's going to look kind of like that. And now, of course, these ones are the easier ones, 6 and 1. So within here, so the 6, and it's positive, so that means it's negative. It's going to move it to the negative direction 6 and up 1. So it's going to shift it this way and up 1. All right, so that's what you're going to have. So let's see visually if we're gonna be able to see that. So let me graph it for you as well. All right, so there you have it. Here's your original one. Okay, that's your x cubed, the blue one. And then here's your shifted one. All right, so the transformations. So we were kind of dead on, or at least I was semi dead on, right? So again, it reflects back in the y, so it flips it over. Okay, so let's work these one by one. I'm gonna just change this just so that you can see, you know, what's happening. Okay, so first, so that was your -1. So notice it reflects it back in the y. Okay, so that's the first one. Then your second one, so now if you do this, it's going to reflect it back again, but now in the x. So it's going to turn back to the same thing. Okay, however, now you're doing it by 0.2. So that's the stretching out in the x. So it's stretching it out in the x. So that's that. Now you're shifting it over. So your h, you're shifting it over, so you shifted that over that way, and then you shifted it up that way. And that was it. All right, I think that's enough torture for you. It's a super long video. All right, we'll see you in a future one. I wonder if you got this one. I'm sure that you're not happy if you were watching the entire thing, but I hope that it was helpful and it forced you to really think outside of the box. Bye, everybody.